Hello. Hello everyone. Am I audible? Can anyone confirm if his voice is clear? Okay. I think let's just get started. This week we will be covering some problem related to the content which was covered in this week. Let me summarize a brief summary of this week content, and then we will go ahead with the problem solving session. So, if you have any doubt related to the problem solving session which we did earlier, or any content related to anything related to the content which we covered, or even discussed in the lecture in last week, you can ask. This week, the main theme of this week content was the impedance matching. So, uh, so like the uh, need to impedance matching is basically like you want to transfer the signal from a transmission line to load, or load which can be antenna, or your receiving antenna, or transmitting antenna, or other transmission line. So basically, to match the load, what you uh, what you consider is, let's say this is jet let's say this is jet 2, has the this, and let's say you want to transfer the this load you want to transfer. So at the end of line, you can write the you can write the expression for input impedance. And basically, if this is the transmission line, you can write the input impedance expression as. So there is there is a case where, if you match an impedance at a particular frequency, then at the other frequency it may not be matched actually. So normally, if you take a single cross section line, so it won't may not may not provide the impedance matching at all the frequency. So let's say if you matched perfectly matched at one frequency, and that, so basically, so you can write this impedance as like the Z2 square by RL, the Z input impedance you can write here. And then like at any other frequency you can write the expression in terms of this. So Z input you can write as Z2 times RL by. So if you want to match the so you can write as and this you want to match to a transmission line of Z1. So that you can write as a RL divided by Z1 plus J times square root of RL by Z1, 10 of pi by 2, and you can write as a beta L in terms of fractional frequency. So pi by so f naught. So basically this f naught is where corresponding to beta L equals to 2 pi. So at f equals to f naught, that beta L equals to not 2 pi, it's pi by 2, corresponding to quarter wave transformer. So that basically, so this is f by f naught, and any other frequency you can write in terms of this general expression. Also in the denominator it will come this RL by Z1 plus J times RL by Z1, 10 of pi by 2 f by f naught. So this is your input impedance, and you can write the reflection coefficient at the input equals to Z in minus 1 divided by Z in plus 1. So then basically like you can write this as like if you simplify the if you match to this line, then you can write as a RL by Z naught Z1 minus 1 divided by RL by Z1 plus 1 plus 2 J times square root of RL by Z1 10 of pi by 2 f by f naught. And if you take the magnitude of this, you will find that magnitude of the reflection coefficient is 1 by square root of 1 plus 4 times z1 rl by rl minus z1 whole square sec of square pi by 2 f by f naught. So now if you write this, so now you can plot this reflection coefficient versus f, or you can this term you can call as a theta also. So you can plot reflection coefficient versus theta also. So if you plot that, so basically what you will happen, like this is because this is the periodic function, you will see like the at f naught. At f naught, this is f naught, this is 2 f naught. This is just wait. So this is so this is f naught, this is 2 f naught, and this is 3 f naught. So similarly you can write this. So if you plot this function, it will be like at f equals to f naught, the reflection coefficient will be minimum, it will be 0, and then at the is it will be maximum, and it will follow like the similarly this. So this as you can see, like the at all the frequency this impedance is not matched. So at f naught, if you have impedance matching, but at the other frequency near around this f naught will not have like complete matching. There is a peak and trough corresponding to that, and for like this the trough actually that is a completely match case, and that this is the mismatch case. So basically, like the and this the bandwidth. So basically, like the what is mean by the bandwidth of the impedance matching? So at like the for a line actually this is there is a threshold value of reflection coefficient which is gamma m, which below which we can apply that this tolerance is acceptable, and the frequency difference corresponding to that is basically defined as your bandwidth of the matching. So based on this threshold level, you can define and this is difference compared to the 3 dB bandwidth. So basically that you can define you can define the uh, uh, you can define the fractional bandwidth or delta theta, and so basically this delta f is known as the delta f by f is basically delta f by f is basically your f by f naught is basically your fractional bandwidth. So this is one of the important term for impedance matching case. So now, like if you take single section lines, so actually that will have very narrow band matching. It won't be possible completely to match a larger set of impedance. So for that, basically, to match a different to match a broadband kind of sources, you need a multi-section transmission line. So the case which we were considering actually, uh, so it will be like if we consider a multiple reflection, let's say this is the input impedance line, that is Z1 impedance, and you have a other line which you want to match, which is Z2, and that this line you want to match to a load. So this is RL. So now what will happen? So at this point, at the load side, the reflection coefficient here is the Z gamma L is basically equals to uh, uh, RL minus Z2 divided by RL plus Z2. Similarly, the reflection coefficient which the here it will be Z2 minus Z1 divided by Z2 plus Z1. So this is the reflection coefficient here. So what will happen? Suppose these lines are not matched. So then basically once you transmit a signal, there will be a reflected signal which will be correspond to z this gamma which will be correspond to gamma 1 times V in, or you can say V plus, and the signal which get transmitted is again reflected back, and that back reflected signal again it will go back, again it will get reflected from this line. So if you consider the multiple reflection, that this see the multiple reflection case, then basically you need to write the total reflection coefficient as sum of the reflection coefficient of the individual line. So if you write that basically, so you can write as so the you can write that you can write that expression actually. So you can write that input impedance as input impedance, which is seen here as gamma 2 1. Basically, that gamma 2 1 is reflection coefficient from 2 to 1 line, plus gamma L times exponential of minus j times 2 beta L divided by 1 plus gamma 2 1 gamma L exponential minus j times 2 beta L. So this is the reflection coefficient if you consider the two line. And when there is not not the when that Z2 approximately equals to Z1, you are considering that these two lines does not have much significant difference in the characteristic impedance. So basically this expression you can simplify. So this this when this is signify like this, then basically this bottom term in this expression becomes insignificant, and you can neglect this with respect to x actually. So what will happen then? Your input impedance will become gamma 2 1 plus gamma L times exponential of minus j times 2 beta n. So this will be the case when your two line has approximately similar characteristic impedance. So then basically like if you can take so you can stack up n different section network. So basically you can have n different sense network. So basically you can uh, similarly you can form this network where this is Z1, this is Z2, and supposedly this is Zn. You n len network you are taking. So so that basically and you are considering the length of this line. Let's simplify the case. That length of this line, so you can count as beta times L1 and equals to beta times L2 equals to beta times L3 equals to theta, which is your basically it's the path length. So then basically you can define this the this so you can define as this is the reflection coefficient at 1. Let's say this is 1. So the reflection you can write as input impedance as the, let's say, reflection coefficient at this is basically gamma in 1. So you can write the input impedance of this line as gamma 1 0. The that is the reflection coefficient at this line at the initial. So at this boundary, basically the reflection coefficient is this gamma 1 0 is basically equals to z2 by z1 divided by z2 plus z1. So then basically you can write this expression as plus gamma in time exponential of j minus j time 2 theta. So this again you can replace this gamma in by again this reflection coefficient based on 2 1, and you can write this will form a n length series, so it will become gamma 1 0 plus gamma 2 1 exponential of minus j time 2 theta plus gamma into exponential of minus j time k theta, and that basically you can write in terms of series equation. So gamma 1 0 as we have defined, gamma k you can define as gamma k plus 1, and k line you can define as z of k plus 1 minus z of k divided by z of k plus 1 plus z of k. This you can define, and basically so this at the and at last Rn plus 1 comma n, you can define Rl minus Zn divided by Zn plus Rn. This is at the boundary. So at this boundary, this is the reflection coefficient. So then basically you can write in terms of like the Z input impedance in terms of uh, reflection coefficient gamma in terms of theta. You can write in the summation k equals to 0 to k equals to n gamma of k plus 1 comma k exponential of minus j times 2k theta, and that basically you can write as sum of gamma k exponential of minus j times 2k theta, k equals to 0 to n, and the center frequency at the center frequency theta equals to pi by 2, and at theta equals to 0 which is at the 0 frequency, that is dc. So the it will form the gamma equals to z k plus 1 it will form the rl minus z naught divided by rl plus z naught expression. So this is the multi-section line. So similarly, based on this, what is the, and you can define the relationship for k. What is the relationship? And for very simplistic case, you can write the expression for each of this. And basically, like there are different kind of transformer exist. So for example, that binomial where your gamma in is form gamma in theta forms the binomial kind of expression it shows. So 1 plus exponential of minus j times 2 theta, and it is a binomial series. And you can also there are higher order of this Chebyshev. So this is uh, Chebyshev polynomial which satisfy this cos of theta equals to cos of n theta kind of expression. These are known as the Chebyshev transformer. So basically in this transformers, actually because of the multiple reflections, there can be different uh, so within this so basically in the this expression is for single single section line, and if you take multiple section line, so it will follow this kind of ripples in the passband. So depending on like if you can tolerate with the higher like Chebyshev and other binomial line, these ripples if you can tolerate, then basically the impedance is matched within your the these if these ripples are smaller than your acceptable tolerance, basically then you can say within this broadband range the impedance is matched. So basically, multi-section lines you can use for the multi-section line you can use for this kind of ripples, and for binomial line the gamma is like this actually. So and for other higher Chebyshev, there are ripples in this, and also that other exponential or tapered line you can have variations of this. So this is the brief summary of the content which was discussed in this. So even that taper you can define in that also. You can there are different kind of tapers are there: exponential taper, triangular taper, those kind of tapers are there. So for that, basically you can define. So yeah, so this was the summary for this week content. So if you have any other doubt, you can ask, or we will start problem solving session if you don't have any doubt. I will wait for some time, then we will start for with the problem solving. Okay, so if you don't have any doubt, so let's just go through the problem solving. So then, which of the following is true? First problem talks about which of the following is true. Single section transformer is used for narrowband impedance matching. Multi-section transfer are used for is used for broadband impedance. This is correct. So you can see in the case of narrowband matching, actually your reflection coefficient versus theta or frequency is this one, and for broadband, this is binomial or Chebyshev kind of impedance matching technique. This kind of like the reflection coefficient versus frequency plot accurate. So if you can tolerate little bit of ripples in the pass band, so this is basically your pass band, which the frequency which you want to pass. This is basically the pass band, and if you can tolerate the some ripples in the your pass band, then basically you can have the broadband impedance matching with multi-section transmission multi-section line. So, this the correct answer for this is basically this single for single section line the like the this is narrowband, and broadband line which is like you can have a larger band for lower reflection coefficient. So that is can be used for broadband impedance matching. So the correct answer is first. Both first and seconds are true. So now let's just move to next problem. So this was straightforward related to the content or lectures from the class. So this so in the figure shown below, A and B are equidistant from the origin of the gamma plane, and A and B can be joined by the straight line passing through the origin. And if the impedance at this is uh, this one, and what is the impedance at point 1? So basically, so this side, so so this side, if you consider as a impedance, so this side, if you consider the impedance, and that if you take the mirror image of this point symmetrically, that will convert it into the admittance. So basically, so if you take if you take if you so if you let's say if you can so any point for this pi by 2 the symmetric point will correspond to admittance, so it will have the same admittance which correspond to the admittance which is opposite. So the y of this side is 0.5 plus j times zero point 0.5. And if you want to calculate, this is the admittance at this point, and if you want to calculate the impedance, so basically that impedance is basically y inverse, and that basically you can take as a zero point 0.5 plus j times zero point 0.5, and you can you can take complex conjugate of the denominator zero point 0.5 minus j times zero point 0.5, and you can write zero point 0.5 minus j times zero point 0.5, and this basically so now you can write this as so now you can write this as so this is or you can write uh, you can write this as one of the this just wait a minute. So, yeah. So now you can write, let's say you take out the zero point 0.5 outside. So yeah, so uh, you take the zero point 0.5, let's say this is 0.5 plus j times 0.5, and you take the 0.5 outside, this is 1 plus j, and that basically you take the complex conjugate and multiply, so this will become 0.5 1 plus j, and this is 1 minus j, and this is 1 minus j. So now it will become the denominator, this is numerator is 1 minus j, divide by uh, zero point 0.5 times, it will become 1 square plus minus j square. So this will become j square is minus 1. So this numerator this term will become 2. So 1 minus j divided by zero point 0.5 times 2, which will be equals to 2 multiplied by zero point 0.5 will become 1 minus j. So the correct answer corresponding to this these choices will be the second one. So yeah, so this was the solution for this. So basically, if you take any point mirror image, that will transform to the admittance. So if here the admittance is given, so if you can take to the mirror image, uh, then it will basically become the impedance circuit. So this was the problem. If you have any doubt, you can ask, or we will move to next problem. I will wait for some time, otherwise we will move. Okay, so with this, let's just move to let's just move to this point, and so basically the input impedance actually you can write as uh, you can write as uh, so Z in you can write as Z naught divided by Z naught divided by your Z1 so ZL plus J times Z naught 10 of beta L for lossless sign divided by Z naught plus J times ZL 10 of beta L. This you can write as the input impedance. And if you take like this uh, for this quarter wave line, you can see like that for quarter wave line, so L equals to 0.525 lambda. So which you can and So basically, for 0.25 lambda, you can write beta L equals to 2 pi by lambda multiplied by 0.25 lambda, and this will become this will become uh, so this lambda will get cancelled and this will become pi by 2. So then your Z in will become Z naught, and 10 pi by 2, 10 pi by 2 is infinity. So this ZL you can neglect. So this times this will become Z naught, J times Z naught 10 of beta L, or this infinity, divide by this second terms also you can neglect. So this ZL 10 of beta L. So this will get cancelled because infinity by infinity form, and this will get cancelled, and your input impedance will become Z naught square by ZL. So that and you can write you can write as like this 0.75 line as so beta L for this will be equals to so it will become 2 pi by lambda times 3 by 4, 0.75 is 3 by 4 times lambda. So you can write as a so you can write as a 2 pi minus pi by 4, and you can write like this will be similar to the pi by 4 line, lambda by 4 line, because 10 2 pi minus pi by 4 equals to 10 pi by 4. So no, just wait. Yeah, this is pi by 2. So this is pi by 2. So so this is 3 pi by 2. You can write as a 2 pi minus pi by 2, and basically like that this 0.75 or 3/4 line also will behave as a as a quarter wave transformer. So basically you can write the input impedance will be similar. So that you can so this is given as load impedance is given at 200 ohm. So the input impedance at here will be equals to 100 multiplied by 100 divided by 200. So this will become 50 ohm. So the input impedance is here is 50 ohm, and then again you can transfer back to the this input. So basically that then it will be equals to this 0 1 line. So Z in will be equals to Z 01 square divided by ZL, which is equals to this Z input impedance at two line Z into, and which is equals to 50 multiplied by 50 divided by 50. So this will become 50 ohm. So the correct answer will be at 50 ohm. So is there any doubt up to now, or any doubt related to content which I covered, or content which were there in this week session? So let's just uh, let's so uh, if there is no doubt, let's just move to uh, uh, let's just move to the let's just move to the like the problem, and basically in this problem basically we need to design uh, a single section transmission line. So basically so in this we need to design single quarter wave transformer, uh, design a single quarter wave transformer to match a 10 ohm load to a 50 ohm transmission line at 3 gigahertz. So that basically so we need to match a so basically so we need to design So this so basically this is like, let's say this is the, so this is load, and you need to design it 50 ohm matching. The input impedance should be equals to the 50 ohm, and this is basically like this is the, let's say Z naught is the characteristic impedance of this line, and ZL is the this load, and this is, let's say this line of this length is L. So basically like this to match a 10 ohm load, this is 10 ohm load, and basically now you can to design this line, basically you need to so you can calculate basically let's say the characteristic impedance of this line is Z naught. So basically you can define as so this and this the length is given. So the quarter wave transformer is given. So at 3 gigahertz, you need to define. So the beta L equals to L is given as lambda by 4, and beta is basically beta is your so beta L you can write 2 pi by lambda times so this so basically you can write this as a generic impedance actually. So at so this you can calculate like so so at the center frequency, basically you can calculate the like the center frequency, basically your beta L equals to pi by 2 and beta L so that basically at the center frequency, this is given as 3 gigahertz. So so you can calculate the lambda corresponding to that 3 gigahertz, and you can calculate the what is the line of length of the line required for this. So basically, lambda you can calculate C by F, and basically this is 3 into 10 power 8 divided by your this is 3 into 10 power 9, and which is equals to point lambda is equals to point also this will become the uh, so this lambda will become this lambda will become like this point 3 into so this will become point so this will become this will become 10, and this will become 1, and this will become point 0.1 meter or 10 centimeter lambda, and then basically you can calculate what is the for single section line, basically center frequency is equals to your beta L equals to pi by 2. So that basically you can define as beta L equals to pi by 2, and you can write like now basically so this is the quarter wave transformer line, and then basically your input impedance is given as uh, Z in is given as Z naught square divided by ZL, and basically that you can define as your the 50 divided by this is Z naught square divided by ZL is 10 ohm, and with this Z naught you can calculate the square root of 50 multiplied by 10, and this will become 10 root 5, and that will be the impedance, and this determine the percentage bandwidth. So basically like you can define the bandwidth as with this you can calculate the bandwidth. So it's basically equals to the bandwidth is equals to bandwidth you can calculate by this equation. So bandwidth you can calculate by this like the tolerance limit. So basically the for the single uh, 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 single section transmission line, this is the gamma m. And at the gamma m, you can calculate the cos of theta m equals to gamma m divided by square root of 1 minus gamma m square, and which will be equals to 2 times square root of z1 or z0 times rl by square root of rl minus z1 mod square. So with this you can calculate the theta m, and you can calculate the delta theta by pi by 2 minus theta m. Theta m you get from this equation. And basically like now the fractional bandwidth delta f by f naught is basically your delta theta by pi by 2. So at the center it is basically pi by 2, and this will become 2 minus 4 times theta m divided by pi by pi. So that basically this problem boils down to calculating this. So we know that Z1. So now with this we can get like with the this expression we can get the value of Z0 or Z1 or Z0, and then basically RL we know and other expression we know. We can get the value of theta m, and basically that we can use you can you that we can you can that you can use to find the fractional bandwidth you can calculate by this expression, and roughly you will get around 29 or 30% fractional bandwidth, and the correct answer closer to this will be the second actually. So this is the this problem. So if you have any doubt, I will pause for some time, and then we'll. If you have no doubt, then we'll start the next problem. So yeah. So now you can that basically you can for you can calculate the for this basically you can calculate for yeah. So this let's just move to next problem. So if four sectional binomial matching transformer is used to match a 12.5 ohm load to a 50 ohm line at the center frequency of this, the bandwidth obtained for this transformer for gamma m equals to this is. So basically like you can calculate so basically for binomial transmission, so binomial matching, the uh, gamma of theta is given as a times exponential of 1 plus exponential of minus j times 2 theta power n, which is n section line, and a is given as 2 to the power minus n ZL minus Z naught divided by ZL plus Z naught. And that basically you can calculate A, and that A so ZL is given, Z naught is given, and four section. So the four section line n equals to 4, and ZL is given as 12.5, and Z naught is given as 50. So this you can calculate A mod of A is equals to 2 to the minus 4 multiply by 12.5 minus 50 divided by 12.5 plus 50, and this mod you can take. So that with this you can calculate mod of A, and the gamma m is given as in the problem. And basically then your gamma m for binomial line is basically 2 to the power n mod of a cos of theta m, cos of n theta m. So that with this theta m you can calculate by this cos inverse half of gamma m. So basically this will be equal to half of gamma m divided by mod of a, and this power 1 by n. So the n equals to 4. So here is n is 4. Gamma s is given. Mod of a we can calculate from here, and that we can calculate the theta m, and the fractional bandwidth delta f by f naught is given as 2 minus 4 theta m divided by pi, and we can plug in the value of theta m here, and that we can calculate the fractional bandwidth with this equation. So if you plug in the value, and you will reach at this third option, which is around 69%. Yeah. So this is the problem. So if there any doubt related to this problem, you can ask, or otherwise we will move for the next problem. Okay, so let's just move to next problem. So in this a three section Chebyshev line, n equals to 3 is given, and used to measure 100 ohm. No? ZL is given as 100 ohm to a 15 ohm line. Z not equals to 50 ohm, and ripple gamma is given, gamma m is given as 0.05. So now for Chebyshev line, the the uh, the for Chebyshev line, gamma of theta is given as a times exponential of minus j times n theta times the Chebyshev of n order sec of theta m times cos of theta. So this is the expression, and a is given by a is given by this zl minus z naught divided by zl plus z naught multiplied by 1 by tn times sec of theta m. So this is your this, and basically now now you know ZL, Z naught, ZL plus Z naught, and Tn sec theta n you can calculate by your expression, and like you can write this expression. If you put in the gamma equation, then sec of theta m you will arrive at cos hyperbolic times 1 by n cos of hyperbolic inverse 1 by gamma m zl minus z naught divided by zl plus z naught. So this is the expression for this. So with this you can calculate the theta m. So gamma m you know, zl you know, z naught you know, this you know, cos hyperbolic you can numerically calculate. N is given as 3, and so all the values are given. So basically you can just take sec inverse of to find the theta m, and the again the fractional bandwidth delta f by f is given by the fractional bandwidth delta f by f naught is given as 2 minus 4 theta m divided by pi, and which you can calculate, and that basically you will find this the fractional bandwidth is around more than like this 100%. So that basically you can use to design the multi section impedance transformer. So mm, if you have any doubt, I will pause for some time. If you can ask uh, for the problem. You can ask if you have any doubt. So let's just move to next problem. So which of the following is true? Chebyshev matching is transformer optimize the bandwidth at the expense of passband return. So what happened is in the binomial matching, if you plot the gamma of theta versus theta, so this center frequency is pi by 2. So if you plot this with respect to your this, then you will see like this kind of variation you will see. And if you take the Chebyshev polynomial or Chebyshev transformer, then basically this roll off is faster, but it will have like this kind of like. So this will have a larger bandwidth, but it has the ripple around your passband. So basically, like the Chebyshev uh, matching transformer gives the larger bandwidth, but there are there are passband ripples in the present in your reflection code. In the binomial case, the passband ripples are not there, but the bandwidth is uh, is uh, is but the bandwidth is small, but the passband ripples are not there. So the second option is incorrect because binomial matching transformer, it says binomial matching transformer optimize the bandwidth at the expense of uh, uh, passband ripples. So no, if the bandwidth is less, it does not optimize the bandwidth, but the bandwidth optimization it happens in the Chebyshev matching. So the only first option is correct, others are wrong. So uh, so next problem talks about which of the following are techniques used for impedance matching. So the quarter wave transformer is also used for narrowband impedance matching. Tapered section is also used for impedance matching, and the binomial transformer are used if you want to use like optimize the ripples at the expense of bandwidth. And also stub matching is also used. You can put the stub matching in the path of your transmission line, either series stub matching or uh, shunt stub matching you can use, and those all the techniques are used for impedance matching. So the correct option is fourth one. So so then basically yeah so so now the this so in the binomial transformer, as the number of section increase, percentage bandwidth will get. So you need to find the trend. So uh, so 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 this theta m in the binomial transformation is given as theta m is given as cos inverse of half of gamma m divided by mod of a times 1 by n. So now if you increase n, so this term will become lower and lower. So it will become this. It will become like gamma by. So it will become so this. So you can write this cos of theta m equals to half of gamma m divided by mod of a, and this cos theta m is less and less. So as you increase this, your theta m will get increased because like this term will become smaller. Uh, so then no no so this term will become, as you increase n, and this term will become smaller, and this total term will become larger, and this theta m will become smaller. and then we basically your this delta f by f naught will be equal to 2 minus 2 minus 4 theta m divided by pi. So as the theta m decrease, your theta m will get decrease, and your passband, the bandwidth will get increase actually. So the percentage bandwidth will get increased. So the correct answer is this. So let's move to next problem. Say a quarter wavelength transformer with the characteristic impedance Z naught is used to match the input impedance of 100 ohm with 50 ohm load. What is the value of Z naught? So the quarter wavelength transformer is given. So Z in basically equals to Z naught squared divided by RL or ZL. So basically, input impedance is 50. Input impedance is 100 ohm, and that is Z naught square divided by RL is 50 ohm, and Z naught is basically square root of 100 multiplied by 50, which is equals to 10 root 5, and which will be equals to uh, your this I think it will become approximately like 70. So this will become square root of 500. That will come around the 70 ohm actually. So that basically, no, this is 50. So this is so this basically you can like this is a simple problem. So, if you have any other doubt related to the problem solving session, you can ask, or if you don't have any doubt, then we can end this session for today. This was the last problem for today. So, we can if you have any doubt, I will be it for some time, and then if you don't have any doubt, then we can say this session for today. I would like to thank you so much for your patiently listening this session. Okay, so if there is no doubt further, so we can end this session for today. We will meet next time, same time in the next class. So till then, thank you so much for listening this session. We will meet you. See you in the same time next week. So yeah, bye. Have a good night. Great learning. Thank you so much.